And so welcome everyone to the evening session of our workshop. So I just mentioned that the talks of the morning session are now online on YouTube, and the links for the talks are on the workshop website. So if you go to schedule or talks, you will see next to the titles of the talk a link. And for everyone in Europe who was not able to attend the morning session, you can go to the recordings that are now available on YouTube. So we are very grateful to have our first speaker of our evening session, Professor David Vegh from Queen Mary, University of London. And he's going to talk to us about the spectral curve of segmented strings. Please go ahead, David.
Thank you, Rak. Thank you very much for the invitation to speak at this great conference. Indeed, so I'm going to talk about segmented strings in anti-de Sitter space, specifically ADS3. And I need to give you some motivation why it's interesting to study strings at all in ADS. So you might be coming from different places. My personal motivation was to study the string worldsheet as a toy model for quantum gravity. So it's 1+1 dimensional theory that lives on the worldsheet. And interestingly, it has local degrees of freedom, unlike, for instance, the Jackie-Teitelbaum theory of gravity. So my first interest arose when I read this paper by Dubovsky and collaborators. And there were interesting new developments in the following years. It turns out that there is a universal bound on chaos on the Lyapunov exponent that I denoted by lambda L. If you look at some chaotic quantum theory at the finite temperature T. And it has been conjectured that black holes are the fastest scramblers in nature. So for them, the Lyapunov exponent is maximal. So it saturates the bound, and this has indeed been computed by Shanker, Stanford, and others via ADS-CFT. Calculations are a bit complicated. They dealt with out-of-time order 4-point functions, which are hard to calculate. And the idea was to calculate it in a simpler model. And we did that with Jan de Boer, Eva Labres from Pedraza a few years ago, and it turns out that even in the string, the worldsheet theory saturates this universal bound. So it has some features, the string worldsheet has some features common with gravity, so it might be interesting to explore this in a bit of detail. Another motivation for studying ADS is studying ADS-CFT. In the planar limit, where you might be interested in solving the sigma model in ADS, ADS 5 cross S5. So that's another direction that you might be coming from. And a third direction is applications of ADS-CFT, where you might want to compute, say, Wilson lines, scattering amplitudes, or other things. I wrote a paper on wave turbulence on the string itself. So there is some interesting phenomenology there as well. Okay, so that's the motivation, and here's our playground, anti-de Sitter space. So I have some pictures which might confuse you if you have not seen this before, and if you have seen it, it might be a bit trivial. But so what is our definition? So let's consider flat space with two time directions, R2, D minus 1, and consider a hyperbolade. So y squared equals to -1. That defines this hyperbolade. And for ADS2, this is this surface in R2, 1. Okay. And in this space, this circular direction is time, so you have to sort of unwrap that in order to get to global ADS. You don't want to have closed time-like loops. Once you do that, you can write down the string equation of motion. the Lagrange multiplier, you can force the string to lie on the surface of this hyperbolade, and you get these equations of motion. You have the equation of motion here, and also you get some Virasoro constraints. So these are quite simple, but I want to point out that this is a nonlinear PDE, so not as simple as you think. But luckily, it's an integrable theory, so that we will use that in what follows. Okay, so a global picture of ADS3, which will be our main interest, is this cylinder here. So the bulk of the cylinder is ADS3, and a time slice. So like this disk here is sort of visible on the right-hand side. It's hyperbolic space, which I will show you some animations with strings moving in this particular space. The boundary is at an infinite distance, so these points are infinitely far away. And finally, this wedge here that you can see, that is the so-called Poincare patch, for which you see a very simple metric here. It's basically, it would be just flat space here in the numerator, but everything is divided by z squared. Basically the space-time has a boundary here, z equals 0. This is the z direction, and you can think of the z direction as some vertical direction. So if you throw up a rock, it will fall back down. Okay, so that's the Poincare patch coordinate system. Okay, so we are interested in studying string motion in this space-time, and this has been done before, started before I was born. So instead of the general solutions, today I'm going to be talking about segmented strings. Okay, so what are segmented strings? You want to build the string from elementary segments. So like sort of like straight segments which have a constant normal vector that you can define in R2,2, because this is a 4-dimensional linear space. So you can take the string embedding vector, 2 tangent vectors, and then you create the perpendicular vector to that. So this normal vector, it does not only tell you about the sort of the configuration of the string, it also tells you about the transverse speed of that string segment. And now here's the idea: glue the string from these simple segments. So just attach segments like which have a constant normal vector. Okay, so this will provide you with a generalization of piecewise linear strings in flat space, which would look like something like this. And obviously the pieces are moving. Okay, so let's see how this what the elementary string segment is in ADS. So here are some pictures. On the left-hand side, you can see again global ADS3, which is this cylinder, and you see a string worksheet in it colored in green. So this surface here, and the string here, this green worksheet connects 2 antipodal points on the surface of the cylinder, so that's denoted by Q and Q bar. And so this is sort of the diagonal on the time slice, and this is static in these coordinates, and it is clearly a solution of the Nambu-Goto equations of motion. So the orange slices are the bottom and top boundaries of the Poincare patch, and you see if you unwrap the surface where it touches the cylinder, you get this Penrose diagram for Minkowski space. And the Q and Q bar quarks or endpoints of the string are these vertical lines. So that means that in Poincare patch coordinates, this is what the motion of the quarks on the boundary. And in the bulk, so again, this is our z direction. Here's the boundary of ADS. Your elementary string solution is a semicircle that comes from infinity, shrinks to a minimal size, and starts expanding again. So in these Poincare patch coordinates, the string is not necessarily static. Okay, and you can now boost this string solution using the SO2,2 isometries of ADS3. Okay, so we have a solution like that on the Poincare patch. So again, this is the boundary of ADS. And I want to attach to it another string segment. So there's a 3-parameter family of solutions. And if we just pick 2 randomly and you try to attach them, then we face a problem. Namely, there are pieces created here, finite length pieces, which then start moving with the speed of light. That's not exactly good because then the corresponding energy will be infinite. So that should not happen. So it turns out that there is one constraint. If you want to attach 2 pieces, let's suppose that you have two segments, this guy here and another one there, and these have constant normal vectors. Say this one is, let me switch to permanent guy, and L, this normal vector, this other piece has an R normal vector. Then it turns out that the condition that these must satisfy is they should multiply to 1. Okay, so that's your only constraint for adjacent string segments. And as a consequence, it turns out that this kink where they are attached, this point has to move with the speed of light. You can also understand that because if it did not move with the speed of light, you could move to a coordinate system where it's sort of static. And obviously, if you have a string configuration like that, it won't stay like that because of the string tension. It will get deformed immediately. And that does not happen if you cannot move to the frame, the rest frame of that kink. Okay, so once you connect many pieces like this, and this third guy, it might happen that the kinks are moving towards each other. So you have to figure out what happens when they collide. Okay, so in this case, I'm presenting this in flat space. You can think of this segment as being static. This is also static, and this middle segment is moving with some velocity v upwards. So eventually, these two kinks will collide when this segment A, whose normal vector is A, it reaches this point. So it turns out that what happens is that V switches sign, so V goes to minus V. There's some time symmetry here, and you can figure out what the new now downward moving A segment, what normal vector it has, and it's given by a reflection formula, which is very simple. So you reflect this A vector on sort of the average of the 2 other normal vectors. So on the actual worksheet, and by the way, please stop me if you have any questions. I'm happy to explain. So this is what happens on the worksheet. So here we have tau and sigma directions. And these lines are the kink word lines at 45-degree angle because they move with the speed of light. And the reflection formula gives you from these 3 normal vectors, it provides you with A prime, the next one. So if you have initial data for these patches, these ADS2 patches, then you can now start evolving your segmented string forward or backward in time. And you can basically describe the string motion this way completely. So I think here I should show you some examples. So let me perhaps go back to Zoom and stop the share, and I share here. And I'm gonna show you a few examples. So this is a basic example, which, again, so can you see the screen?
Yes.
Okay, great. So what you see here is the Poincare patch, VDS3. Here is the boundary, this top line here. And here is a segmented string consisting of 3 segments. This is one of them. This middle piece, this big one, is the second one, and there is another one here. And this red and gray dot, these are the kinks where the segments are connected. There are some ticks here which are sort of some projections of the normal vector. It doesn't really matter. And you let it evolve in time. So you see this middle segment is on this dotted circle, and when the kinks collide, the normal vector changes and it leaves this original dotted circle. Okay, so that's one simple example for a kink collision, and this is an exact solution to the non-Goto equations of motion. Here's a slightly more complicated example with 150 kinks. So they also collide, and you can figure out the time evolution. And from far away, you don't even notice that this is a segmented string because it sort of looks smooth. The individual kinks are tiny. Here is another animation. You can approximate static strings. Oops, what happened here? This dashed line is just a static string that hangs from the boundary as you're holding two endpoints fixed. You can approximate that using segmented strings as well, where now you have a highly non-static string with kinks on it moving with the speed of light. And here's an even more complicated example where this string, I think, consists of at least 500 segments, and I perturbed one of the endpoints. So this is another example for, well, basically for the power of integrability. This is an exact solution as well. And you can continue this simulation for arbitrarily long time because there is no accumulating error when you're solving the equations. It's really just doing the reflection formula over and over again. And finally, I am going to show you another animation now in global ADS 3. These are the time slices. So this is the simplest closed string that you can draw. This consists of 4 segments, and its motion is sort of periodic in time. It just keeps oscillating like that. So we're going to compute the spectral curve for this particular segmented string. Have any questions at this point? If not, let me go back to the talk. And let's just say about all of this that you can approximate any smooth string using segmented strings. I don't really have a mathematical proof for it, but it is sort of true. And segmented strings form a dense set in the space of all string solutions, so you might as well restrict your attention to these objects. So here's a sort of a procedure how to approximate a smooth string whose worksheet is this yellow or golden surface. You pick a time slice on it, then you pick some points, some sort of lattice spacing between them, and then you draw the forward pointing light cones, these gray cones here, and they intersect each other and the surface, these few points, and then you just simply connect the P and the Q points, and that will provide you with the zigzag, which is a good set of initial conditions for your segmented string. So if you decrease this distance between the points, then you approximate the string to better and better accuracy. Okay, so let me say a few words about a different description, which is actually better suited for all the calculations. Here is the string worksheet. So this is again tau and sigma coordinates in the worksheet. And what you see are 4 kink lines. And here there are collision points that I denoted by V, the vertices of this diamond. So these V's are all in R2, 2. So that's the linear space. So I'm allowed to subtract points from each other. So you can take, say, V0, 1 minus V0, 0, and that gives you this P1 vector in R2, 2. Now you can sort of rotate these P vectors at 90-degree angle, and now you can think of this diagram as describing some 2-to-2 particle scattering. And if you're interested in the string action, which is basically just the area of this diamond here, then you can write down the area in terms of the Mandelstam variables, S and U, and you can compute what this means in terms of these difference vectors P, and you arrive at a formula that is very simple. It's log of some differences of these P vectors. Now, what do we know about the P's? We know that they are null vectors because the kinks move with the speed of light. So you can use the spinor helicity formalism, and you write these P vectors, these difference vectors, as a product of two component spinors. So this lambda A and lambda tilde A dot. And you can rewrite the action, so the area of the diamond, using these lambda spinors, these two component spinors. And it turns out that the lambda tilde guys, you can get rid of it, and only the lambdas will participate in this expression, and this is basically given by this kind of a cross ratio. Okay, so if I told you lambda is a real two-component spinor, so it has this lambda u and lambda d components, and you see that, for instance, lambda 1 appears in the numerator. It also appears in the denominator, so its length cancels from the formula. Only the ratio of the components will appear, which I denoted by A. And in terms of these A's, the expression for the area is even simpler. So this is really just these cross ratios of these A numbers. And this is the area of this patch. There are other patches connected to this one, other ADS2 patches, etc. You can compute all their areas, add them up, you get the total action. And once you have the total action, you can derive an equation of motion for these A so-called celestial variables. Okay, so here's the result. And here's the equation of motion for these A variables. So let's just summarize. You take this kink line, which is this, compute this difference vector in R2, 2. And if this difference vector has these coordinates, you can now express the celestial variable as this ratio of the components. And you put this A on top of the edge, okay, on the worksheet. So you see that you have these A numbers, these celestial variables on every single edge in this kink lattice. So these A numbers form a square lattice that I parameterize by I and J, and they satisfy this very simple but nonlinear equation of motion. Okay, so once you have the equation of motion, you can give, for instance, 2 rows. So you see 5 guys are related by that equation of motion. So from 4, you can compute the 5th one. This means that if the enemy gives you 2 rows of these celestial variables, then you can now start the time evolution and compute everything. Okay, but what do we do with these celestial variables? Can you reconstruct the string embedding from these? It turns out that you can, using a very simple matrix that you can write down explicitly. So what you see here now on the left-hand side is the artist's impression of a closed string worksheet. And as you go around the string like that, you go from this P point to the same P points, so P prime is the same as P. These two lines should be identified. And let's concentrate on just these two rows of celestial variables and the kink lines between them. So once this P is given, and you know all the celestial variables, so for instance, B1 and W1, you can compute the neighboring normal vector N1 using the simple matrix multiplication. And from N1 and these two celestial variables, you can compute Q, this position vector, and you can continue. So you can compute all the vertices of the segmented string. So you get back the embedding. So the celestial variables contain all the information up to a global SL2 transformation. Once you know all the celestial variables, you know the string embedding. Let me skip this slide. Let's now talk about the spectral curve. So that's a very important invariant for integrable models. And you can just take a brute force approach and try to compute the spectral curve for segmented strings. So using the polynomial reduction, you can massage the equations of motion for the alpha, which is sort of the area density on the worldsheet. And you arrive at the Singe-Gordon equation. Lux matrices are known. You can write them down explicitly. And you want to solve an auxiliary linear problem to figure out the monodromy as you go around the string. Okay, so once you have these solutions to this linear problem, you can also reconstruct the string embedding using some very simple formulas. So in general, this is a hard problem, and many people have done a lot of work solving these equations. Luckily, for the string, the situation is slightly simpler because you put together the string from very simple elementary ADS2 segments. So you can easily compute the spinor solutions on different patches, and then you match the solutions, and then you construct the global spinor solution on the worldsheet. So this is really not important, but this would be sort of the spinor solution on an ADS2 patch. And it turns out that here, so here's the ADS2 patch, the middle here of this diamond. And it turns out that you want to match it to another spinor solution, which lives on the vertex. So here in the second picture, I blew up the vertex region. So now it has a finite area in this new coordinate system. So this was just a conformal transformation. So there is some kind of duality. So what is the ADS2 patch? So I told you that this patch has a constant normal vector. What is the vertex? The vertex patch has a constant embedding vector. So there is some interesting duality here. And in fact, once you figure out the ADS2 patch spinor solution, it's very easy to write down the vertex spinor patch solution, and you can match them to each other. It's you're not matching constant functions. Everything is a function of z and z bar on the worksheet. So this is some kind of matched asymptotic expansion that you are secretly doing. The result of the matching is the discrete Lux matrix. So this zeta is a spectral parameter here, and the B and W superscripts or subscripts here are the two celestial variables which live on adjacent kink word lines. Okay, so this omega matrix, this 2x2 matrix, will tell you how to go from this point to that point. What is the SL2 transformation that you have to do on the spinors? It has some properties. So this is a determinant 1 matrix. And if you set zeta equal 1, then it becomes the identity matrix. So once you have that, you can now construct the monodromy of the closed string. So here is again our closed string, the worksheet with the kink lines. And you just have to multiply all these omega matrices. So for instance, going from this vertex to this patch here, you write down omega B1, W1, and going from here to here, you write down the inverse of the omega matrix, which now contains B2 and W2, etc. And as you go around the string, you get this final omega of zeta monodromy matrix. Okay, so from that, you know everything. Quasi-momentum, you can write down the spectral curve. Now, something I have not told you up to this point is that for generic values of the celestial variables, these are real 2n real numbers, the string will not close. So the situation will be sort of like this. There will be some SL2 monodromy, so the string will look more like a helix, not a closed string. If you want to avoid that situation, it turns out that it is enough to demand that this omega monodromy matrix, the special value for the spectral parameter at zeta equal I, this should be the identity matrix. So this gives three constraints on the celestial variables. So instead of 2n numbers, you now have 2n minus 3, which will then give you a closed string solution. Here's a simple example for the closed string that I showed you in the animation. Also, the worksheet is on the right-hand side. And again, these dashed lines should be identified. And you have 8 celestial variables, but remember only 5 of them can be chosen arbitrarily. So you can express, for instance, B3, B4, and W4 from the other 5. And you can write down the monodromy, and it just this matrix is just the product of these two omega matrices. Very simple. And if you want to sort of parameterize this closed string, it only has one invariant parameter, basically the size of it. So that I denoted by R, small r. And once you write down, say, the cosine of the quasi-momentum, this r, the length will show up in the formula. And the expression is rather simple. So here I used x for the spectral parameter, which is related to zeta by a simple transformation. So with this procedure, you can now write down the spectral curve for any segmented string, closed segmented string in ADS3. And as I told you, these are basically completely generic solutions in the sense that they can approximate any string solution to arbitrary accuracy. Okay, so this was maybe a bit too technical, but you can do it. And today I would also like to tell you about another way of computing the spectral curve for segmented strings. How much time do I have, Rak?
You have about 5
minutes.
Yeah.
Okay. So, and I'm very happy to talk about this because it goes back to the work I did with Ami Hanani, Seba Franco, and others 17 years ago. My goodness. It has to do with brain tilings. So what are brain tilings? Here's a picture, a particular brain tiling, an example. These are bipartite graphs, which means that you can color the nodes black and white, and black nodes are only connected to white nodes and vice versa. And brain tilings are also periodic, double periodic graphs. So see, there's a fundamental cell here that you can use in red. You can think of them as just a bipartite graph drawn on the surface of a torus. Okay, the dual graph is the quiver, and in the context of n equal 1 for the supersymmetric gauge theories, the tiling also encoded the superpotential. So the vertices gave you terms in the superpotential. So this was discovered in this paper with my collaborators. Okay, these graphs are related to on-shell diagrams, if you're familiar with that story of Nimas and others. Those are sort of cousins. They're not necessarily bipartite, and they're also planar graphs, but they're basically the same. From the tiling, you can compute some kind of invariant object, which was back in the unequal one story. It was the toric diagram of a certain Calabi-Yau, non-compact Calabi-Yau threefolds. For us, these diagrams will be the Newton polygons of the spectral curves of the integrable models. And these are invariant under certain transformations. So this one is the interesting one. This has many names: spider moves, or urban renewal, Postnikov moves, or in this context, cyber duality. And there is another slightly simpler transformation that you can apply on the tiling. How do you compute this invariant object from the tiling? Well, you basically construct some kind of an adjacency matrix, which goes under the name of the Castellan matrix. So the rows and the columns of this matrix are labeled by the black and white vertices. And you write a 0 in the matrix if there is no edge connecting those two vertices, or otherwise you write a +1, perhaps with a minus sign. The details are not important. When you cross the boundary, then you write an X or X inverse, if depending on the orientation of the edge. And when you cross the other boundary, you dress the edge by some other way to Y. Okay, so you fill this matrix, you compute the determinant, and that gives you a Laurent polynomial whose Newton polygon is this object I drew. It's a bit technical, but pretty straightforward procedure. And then there's a seminal paper by Goncharov and Kenyon 11 years ago. They discovered that there is an associated integrable system corresponding to these brain tilings, these bipartite graphs. The dynamical variables of the integrable model are oriented edge loops in the tiling. So for instance, here's one, such a loop, this zigzag here, or you can also have closed ones, these variables corresponding to tiling faces. And I denoted them by Fi for four tiling faces in this particular tiling. And there are two non-trivial loops that I denote by Fx and Fy. So this was one of the non-trivial loops, and the other one could be, say, this one. You can write down the Poisson brackets explicitly, and these are these quadratic brackets. And these epsilon and these epsilon xy, these tell you about the number of edges which appear in both loops. And these other numbers are just intersection numbers of the loops. It turns out that there are enough Hamiltonians that you can define and enough Casimirs for you to conclude that the model is integrable. Okay, so this is the generic case, but which tilings correspond to segmented strings? And here I'm just gonna tell you the result. So these are what we call the YN0 brain tilings. They're basically just here. These are just the square lattice with a slightly bigger fundamental domain. And for a segmented string with n segments, the tiling will have 2n squares in it. The dynamical variables can be directly related to the celestial variables, those A, I, J numbers that I told you about, by taking some cross ratios. What is time evolution? So segmented strings, of course, evolve in time. What does that time evolution correspond to here? Well, it turns out that the spider moves, or aka cluster transformations on the tiling, will be equivalent to our time evolution on the string. And they can be explicitly worked out what that means for the dynamical variables, this Q and P numbers. And this is the transformation. And you can check explicitly that indeed this is compatible with the equation of motion for the celestial fields. And finally, the determinant of some dressed Castellan matrix gives you the spectral curve. Okay, so there's a pretty straightforward procedure to compute that. And I think I'm running out of time, so here's just the last slide. The example with 4 segments. Here's the corresponding brain tiling. It now only has 4 + 4, so 8 faces. You can compute the spectral curve using this procedure that I just told you about. And it turns out that it does match the calculation that you obtained using the omega matrices. Okay, the relationship between the spectral parameters is the square root function. If you draw now the Newton polygon of the spectral curve, you end up with this diagram. So there are these 2 empty circles here, which means that the corresponding coefficients are 0 in the spectral curve. So that's a direct consequence of the fact that the string has to close. So this configuration is not allowed. If you did not have this extra constraint, the integrable model that you ended up with would be the relativistic total lattice. So that is well known, nice quantum integrable theory. With these extra constraints, you get segmented strings. So that's the difference. And here's my summary page. So we discussed a bosonic string in ADS3, and we applied an exact discretization procedure on these objects. And then we rewrote the equations in terms of celestial variables. And finally, we computed the spectral curve using brain tiling technology. There are a bunch of interesting questions. Firstly, how to quantize segmented strings. Can you do that in ADS3? Maybe not. You should be able to do that in ADS5 cross S5 if you also include fermions, but I don't know how to generalize it to higher dimensional ADS at the moment. And finally, if you are interested in the worksheet as 2D theory of quantum gravity, is there a holographic dual to it? In quote marks, obviously, because there are no black holes on the string. But it would be interesting to see if there is some kind of matrix model, perhaps, that is dual to these strings. Okay, so I should stop here. Thank you.
Thank you very much, David, for the very interesting talk. Are there any questions in the audience?